Welcome to a lesson with Dr. Powell. Let's take a look at how we can take a recursive equation or formula and turn it into a non-recursive one. We're going to use a linear transformation perspective, or a module homomorphism perspective. So what we're going to do, first of all, is rewrite this recursive equation this way, where we have n squared on one side and everything else on the other side. Now think about a sub n as being like the sequence. Okay, so the sequence is like a function here, all right? And this is like a shift of the function, a fifth shift of the sequence, and another shift of the sequence. Now when you shift a sequence, think about if you have two sequences and you add them together and then you shift them, it's the same as if you shifted each one separately and then added them together. And so that means actually the process of shifting is an additive function. In fact, it's even scalable. It's a homomorphism. It's a linear transformation in this case, if we're thinking about our scalars as being real numbers. So so this right here, just the act of this shift is a linear transformation, and this one. And then we're adding different linear transformations together with different multiples, and multiplying them still gives you a linear transformation. This whole thing right here, so if I thought of a function going from the sequence a sub n to this right here, that's a linear transformation. We're going to call it L. Okay, so L of f, that's what this side is equal to this sequence over here, and we'll just call it g. So really, we have a nice function, and in particular it's additive, where the output is g. So if we're looking for f, we're looking for we're looking at the fiber of this function over g, everything that maps to g, okay? And so f is going to be in there, so let's take a look and see what this fiber looks like. Now, since L is an additive function, its fibers are just shifts of each other. Shifts, in particular, of the fiber over 0, the kernel. Okay, so a shift of the kernel. So our task is in two parts. We need to find the particular sequence that we can add to it, because sequences are the elements of domain and codomain here of this function L, or this linear transformation L. And we want to find the shifting element, and then we want to find what the kernel looks like. Let's first focus on the kernel. Okay, now the kernel happens when the output of this, so L, so this part, is equal to 0. So 0 on that side. That's the same thing as looking at this recursive equation up here, looking at just this part. This part right here can be written in terms of a matrix. Think about right here. So 0, 1, we'll pick out this element. Think of row interpretation. So how do you pick this up? Notice it's kind of shifting. So this, and then we kind of shift forward in the sequence 1, but in pairs. And the act of doing that, if you're thinking row interpretation, just this picks out that guy. So that's that part. This row right here, notice what it does. It says 3 times that plus 2 times that. That's exactly what we have here, and that should be a sub n. So that's our matrix. Now, if we think about the variable x, oftentimes people use lambda, but I'm just going to use x here. If we think about this matrix as being the same thing as a scalar x, so its action is going to be the same thing as multiplication by x. Multiplication by x could also be written this way. So we're saying that these two multiplications are the exact same. So if we take the difference of these two, I call that the zero action matrix. That should represent the zero action. So thinking of this matrix as giving an action, this would be like a zero action, setting everything to 0 if we multiply by it. Now, the determinant of the zero action matrix is actually equal to 0, and that that takes a little bit of thought to actually see why that's true. I'm not going to discuss that right now, but I mean, intuitively, dumbly, you could say, well, yeah, the determinant of the zero matrix is 0, but it's a little bit more than that, because we're thinking about columns equating, and entries are kind of funny, so it takes a little bit more work. But anyways, if we take a look right here, we have x squared minus 2x minus 3 is equal to 0. That's kind of where we're at. Now, how is that helpful? Think about what x means. X means is like this matrix, and it represents the shifting mechanism of the sequence, how we go from like 2 spots to the next 2 spots, okay? And we're going to use that as we go along. All right, so we can this guy actually factors in this case, x minus 3 and x plus 1. So think about what this means. Think about everything as being like an action on a vector with two components. So 1 could be represented by a matrix with 1's down the diagonal, just the identity matrix. Negative 3 could be represented by like negative 3, that matrix. So basically what we're doing is we're taking the matrix X and subtracting 3 down the diagonal. Okay, let's just look at that here. So we take this guy and subtract 3 down the diagonal. And so we would get, we got 0, 1. So we got, so for starters, we had 0, 1, 3, 2 was our matrix. And we're going to take this and this part right here, we subtract 3's down the diagonal. Minus 3, minus 1, we get a 1 and a 3. X plus 1, think of the same thing. You get a 1, 3, 1, 3. Now let's take a look at this. If I have something in the output of this matrix, x plus 1, so namely something, what comes out of it in column interpretation would be some linear combination of the columns, so basically something with the 1, 3 in it. Well, what does that mean? That means at one point in my sequence, I'm starting with a 1 and then I'm going to 3. Okay, so I start with a 1 and 3. Now what happens further in the sequence? Let's think about that. So if something comes out of this, guess what? If I have the action of x minus 3 on that, this total action is 0, meaning that if I act with x minus 3 on something that already was acting on by x plus 1, I'm going to get out 0, meaning x minus 3 is going to act as a 0 action on that. Well, in particular, that means that x acting on this is the exact same as 3 acting on it. So anything that comes out of here, okay, so starting with a 1, 3, is basically going to be the same thing as saying you multiply by 3 every time you shift forward, so that's the sequence is 3 to the n. You could say that. So you have a sequence of 3 to the n, and that is actually going to be in the kernel. It's represented by this shifting mechanism. Okay, so as the sequence 3 to the n is represented by this shifting mechanism, anything represented by the shifting mechanism x is in the kernel. So we have something in the kernel, 3 to the n. Using a similar idea, thinking about something that comes out of this guy, like 1, negative 1, it's going to be acted on by so x plus 1 is going to behave like 0, meaning that x is going to behave like multiplication by negative 1. So we could even think, okay, negative 1 to the n, that's a sequence that's also represented by this shifting mechanism, so it's therefore in the kernel. I have 2 different sequences in the kernel. Now, realize when we're looking at this, what do our sequences depend on if they're represented by this shifting mechanism, where x is a one specific matrix? It really depends on where you start, right? So you start, there's 2 different places to start. So you can start like, think A0, A1, you have different places you can start. This has a dimension of 2. And so if you have 2 different sequences, and if these sequences are linearly independent from each other, And if you take a look at this, I mean, they start at 1, 3 and 1, negative 1 just at the beginning. If you list those out, those are linearly independent vectors. We're good. That means these sequences would be linearly independent because, you know, just looking at combinations of the first two entries, I mean, that's going to correspond to things beyond as well. So we've actually established that we have a basis for the kernel. It's really just this guy and this guy. I mean, in general, what you do, just kind of backtracking to be a little faster, I mean, basically what you do is you get the characteristic polynomial. Well, that's what this is. That's called a characteristic polynomial for your shifting matrix. But you could get that pretty quick. Notice you kind of see it right here. Think of replacing this guy with x squared, and a sub n minus 1 is the next shift down. So think minus 2x minus 3. Hey, it's all right here, right? Okay, so you could even just look at this and get that polynomial. Then once you got that polynomial, you go ahead, you factor it, you get a couple different values, 3 and a negative 1, and boom, we have, I'm using this notation for span, okay? So these are two sequences in the kernel that span the kernel. So we're done with the kernel, really. That wasn't too hard. That goes pretty fast. Okay, but we just kind of wanted to understand kind of where it was coming from and what was going on with it. Now let's look at what we need for the particular solution, the shift. All right, so how are we going to deal with that? Okay, so we know it's, so L, we're going to put something into L, and we're going to get out n squared. So what are we put into L? What is L? It's like shifts. It's linear combinations of shifts. So you're going to take shifts of a sequence and a linear combination of them and end up getting n squared. So what kinds of sequences could you start off with, or could you shift in order to get an n squared? It makes sense that you're going to be focusing on polynomials up to degree 2. In fact, let's just kind of look at that. So since L is a linear transformation, we could say, okay, we're going to take some multiple of like L of n squared plus some multiple of L of n plus some multiple of L of 1, and we want to end up getting n squared, right? And so we just got to find maybe what multiples we're using, put those inside of L, and then we have L, and then we have that multiple times n squared plus that multiple times n plus that multiple times 1. You know, you just got to figure out what those guys are, and if it works, is that going to end up getting n squared? So what you start with here just kind of depends on what you're given. Just kind of think, okay, well, what possibilities do I have? And if you don't have enough to actually get here, you just put more in until you actually get there. So it's kind of a guess and check type thing. But it's actually not too bad. Let's just think about this. Well, if we were to compute using our definition of L of n squared, we'd get this. L of n, we'd get that. L of 1, we'd get this. Okay? So, so then using that, we think, okay, what do we need we want all this to add to n squared. Let's just focus right here, okay? What do we need to multiply this by, this top guy by right here, so that our leading term will be an n squared? Well, we just negative fourth. It's pretty simple. So negative fourth times all of that. All right. So if you multiply negative fourth in here, what would you end up getting? You get a negative 4. We want a 0 down here, so it looks like we're going to have to multiply this middle guy by negative 1. See how fast that goes. All right, so if that negative 1 is multiplied, so let's see, negative fourth multiplied in right there. Think of that as 14 fourths or 7 halves, positive 7 halves. So think positive 7 halves there. So think of that as negative 8. Okay, so you have, and you want to end up getting 0 down here. Okay, and so what would we end up getting? And so we have 7 halves minus 8. So we can think about 8 as being negative 16 halves. So 7 minus, so we have 7 minus 16 halves, so minus 9 halves. So you have minus 9 halves minus 4 times something is going to be equal to 0, right? Okay, so you can, add the 9, or that was a 9 halves, sorry. Okay, minus 9 halves. So minus 9 halves minus 4 times something is equal to 0. All right, so we have 9 halves on this side is equal to negative 4 times something. You can divide that over, and you have to get a negative 9 eighths. Okay, so negative 9 eighths, well, there we go. These are our constants that we need. Negative 9 eighths, negative 1, and negative a fourth. All right, so then if we go 1, and yes, that's what I have here. Okay, so this is our particular solution. Oh, well, this is a little bit ahead here, but yeah, how did we get this? Well, notice at the beginning here, our goal was to get this for a sub 0 is equal to 1 and a1 is equal to 1. That actually determines which element in the kernel we're going to use, all right? The particular is going to be fixed. It's just going to be something. But then how do we vary it up for our initial conditions right here? It's by changing which kernel element we're going to be using. That's going to change the initial conditions. All right, so we've got to find an element in the kernel that'll work. Notice that this element is in the kernel. The kernel were sequences that were linear combinations of 3 to the n and negative 1 to the n. Okay, so we need to find something in there. We can think, okay, a times that plus b times, b times this. We want to pick something here plus this particular solution. Okay, and we want to choose constants a and b such that when we plug in n is 0, we end up so we get when we plug in n is 0, we're going to get out 0. When we plug in 1, we're going to get out 1. All right, because that's the initial conditions that we were given. So if we do that and we work it out, we actually get this guy right here, which is in the kernel. And that would be it. That is how we can go about a little description of a little bit of why it works and how we can get to the solution of get a non-recursive formula instead of a recursive one. Thanks for watching.